Hello everyone, welcome back. So what we are talking about today is measuring the distances to stars. Now if you recall it's been 2 weeks, but last lesson, we talked about the difference between apparent brightness and luminosity. We measure the apparent brightness from Earth, which is what we see when we look at stars from Earth. But the luminosity tells us how intrinsically bright, how much light this star is putting out. And to find the luminosity, we need to know the apparent brightness and the distance. Which means we need to figure out how to measure distances to stars without using, a luminosity. So what we're going to do today is talk about how to do that. We're going to review that using angles to measure the sky. We're going to talk about using parallax. We're going to define a parsec, and we're going to practice using this phenomenon of parallax to measure the distance to stars. So just to review, in Unit 1 we talked about the celestial sphere model, that all stars are really, really far away, so we pretend they're all the same distance and they're painted on this giant imaginary sphere. And that meant that since we didn't know how far away that giant imaginary sphere was, and we just assumed it was just really, really far, we measured where things were by angles. And you can also use this to measure, for instance, how big something is or how far away two things are. So this person is looking at the moon. And if they draw their line of sight from them to one side of the moon, and then a line of sight from them to the other side of the moon, the angle between those two lines is 1/2 degree. So we say the moon is 1/2 degree angular size. And we can do this with two stars. We can draw a line of sight from the star to us, draw a line of sight from the second star to us. The angle between them is the star's angular separation. And you can do this with any amount of objects. So remember, astronomers, when we don't know how far away something is, we measure their angular separation, and then when we get the distance, we can get the real separation. So, all right, we measure angles. And one way this is useful is related to something that you've probably experienced in your day-to-day life, which is this idea of depth perception. Most of you have two eyes that work, and each of your eyes gets a slightly different view of the universe. For instance, if you're holding your hand right in front of your face, you can notice that through one eye, your hand is in front of slightly different things than when you look at it through the other eye. And your brain automatically learns to interpret that as, oh, this object is very close to me. If you move your hand at arm's length, the difference between what your hand is in front of through one eye and the other eye is much less. So your brain says, oh, this is much farther away from me. This is how, for instance, 3D movies work, is that gives your eyes two slightly different images, which your brain interprets as a three-dimensional view. So we can do this using the Earth. For small-scale things, we can measure from different locations of the Earth at the same time. But there's a way to get even bigger baseline, which is if we look at the same object from one side of the Earth's orbit to another, we can figure out how far away it is. So, all right, let's draw this picture. This is not a scale picture. But we have the Earth's orbit, 1 astronomical unit from the Earth to the Sun, and we're looking at a group of stars, and we've color-coded the one we're going to focus on in purple. Now, that group of stars is some unknown distance d away. Stars are much farther away than the sun is. The distance between the Earth and the star and the distance between the sun and the star are pretty much the same. All right, so let's observe this star. Now, when we look at it from July, I have a little view at the top of what we see, and you can see it's near the rightmost star. Then 6 months later, the Earth has moved 2 astronomical units to the other side of the sun. It now appears next to the leftmost star of this little background group. So this is similar to having two eyes, it's just we can't get a simultaneous view, which works out fine because the stars are not moving particularly fast. So we call this phenomenon parallax. And the angle there that the Earth star sun makes is called the parallax angle, P. So P is basically half the angular distance that the star moves over 1 year. You can see the star moves 2P from January to July. And so we measure that angle. We basically make very detailed measurements of where all those stars are, and we do it over many months so we can capture the whole movement. And then we use trigonometry to work out what D is, because we know what the distance between the Earth and Sun is. It's 1 AU. Now, in this diagram, P is pretty big, and that's because we want to show you what's going on. But in reality, P is very small. If you recall when we were talking about solar system models, heliocentric versus geocentric, one of the things the geocentric proponents pointed out was the stars don't move from month to month, or rather they all move in aggregate on this celestial sphere. They don't move relative to one another, and we would expect that if the Earth was moving. The ancient Greeks understood what parallax was. Now, what's actually going on is they are moving. It's very, very small angle. We need much, much smaller than a degree. So we need telescopes to be able to see it. So what do we call something that's a subdegree? Well, normally we even recall a circle is 360 degrees across. But we can subdivide a degree. A degree has 60 arc minutes, and then an arc minute has 60 arc seconds. And if we need angles that are even smaller, we can start adding metric prefixes. So we can say, well, a milli-arc second is 1,000th of an arc second. And yes, astronomers do use milli-arc seconds and micro-arc seconds. We can make some really precise measurements nowadays. So we're going to focus on arc seconds. So that's 1/3,600th of a degree. In particular, there's no star that has a parallax angle that is larger than 1 arc second, besides the sun, of course. All stars have a parallax angle of less than 1 arc second, as seen from Earth. No wonder the ancient Greeks didn't find it. So what we do is we can use this, that we measure parallax angles that are all fractions of an arc second. So we define a distance unit called the parsec. The parsec is the distance at which a star would have a parallax angle of 1 arc second, parsec. This was particularly useful because, again, just like we measure things in astronomical units, because basically ties everything to one constant, the Earth-Sun distance. And then if we get a better measurement of that, we don't have to change all our numbers, just change how we convert them to standard units like meters. So a parallax arc second, a parsec, is tied to 1 AU. It's 206,265 times the distance between the Earth and the Sun. In real units, that's about 3.26 light years. So it means a star 1 parsec away, light takes 3.25 years to get to the star, from the star to us, or from us to the star. Now, what happens is, as the distance for the star increases, that angle P gets smaller. And it turns out the parallax angle, P, is inversely proportional to the distance D. So a star that has a parallax angle of 1 arc second is 1 parsec away. A star that has a parallax angle of half an arc second is 2 parsecs away. A star that has a parallax angle of 1/3 of an arc second is 3 parsecs away, and so on, and so on. So if you know the parallax angle, you can very quickly determine how many parsecs away the star is. So let's talk a little bit about what we've learned about the nearest stars. No known star is within 1 parsec of the Sun. The closest star to Earth is called Proxima Centauri. It's about 1.3 parsecs away. Now, Proxima Centauri is not visible from the northern hemisphere and not visible without a telescope. It's a very little faint star. It orbits two other stars, Alpha Centauri A and Alpha Centauri B, which are visible from the southern hemisphere. Now, the first star we've measured the parallax of was a star in the northern hemisphere called 61 Cygni. Its parallax angle was about a third of an arcsecond, a little less. And this got a distance of about 3.5 parsecs. So this is a really difficult measurement to do and wasn't done till the 1830s. Measuring this angle even with a telescope is very challenging. But it did let us start to make a 3D map of our nearest neighborhood. So within 5 parsecs of the sun, there's a little over 50 star systems, which make up 63 stars. Stars can orbit one another. Our sun is a singleton, but our nearest neighbor, Alpha Centauri system, is a triple. Of those 63 stars, 4 are bright stars. They are very easily seen with the naked eye. One of them is Sirius A, which is the brightest star in the night sky. We also have Procyon A. Both of those are visible right now. And again, Alpha Centauri A and B, which are only visible in the southern hemisphere. Now, 5 more of those stars are conceivably visible to the unaided eye, depending if you're at a dark place, but don't look like anything special to the unaided eye. Tau Ceti, Epsilon Eridani, Epsilon Indi A, and 61 Cygni A and B. Those the first star we measured. And most of these stars are very faint. Even though they're our nearest neighbors, we can't see them without a telescope. They're stars we call red dwarfs, white dwarfs, and brown dwarfs. Dwarfs because they're all very small. And we're going to talk more about what a red dwarf is, what a white dwarf is, what a brown dwarf is later in the term. Now, we've gotten much better at measuring this, and this is one of the things we do with space telescopes, because space telescopes don't have to deal with the Earth's atmosphere, and they don't have to deal with the Earth, with anything moving the telescope around, whether it be the Earth or even just astronomers walking about. So the European Space Agency put together the High Precision Parallax Collecting Satellite, or HIPARCOS, to make a catalog of bright stars out to 1,000 parsecs. Remember, those are seeing angles of 1,000th of an arcsecond. And the follow-up mission is called Gaia, and it's currently making a survey of stars out to 50,000 parsecs, which is a good fraction of the Milky Way galaxy. The main weakness with Gaia is not measuring parallax of stuff too small for it to see. It's that stars need to be a certain brightness before it can successfully measure their parallax, and 50,000 parsecs means that stars are very faint, even really bright stars. So, in summary, parallax is the apparent movement of an object against the background due to the movement of the observer. It's distance dependent, so we can use it to measure distance. If we measure a small parallax angle or a 0 parallax angle, that tells us the star is really far away. A larger parallax angle tells us the star is nearby. Astronomers use a special unit called a parsec to measure star distances, and a parsec is the distance that a star would be if the parallax angle was 1 arcsecond. So next class, we are going to talk about the colors of stars and estimating luminosity, which gives us a way to measure distance without parallax.